Hello, welcome to part 2 of Chemistry AQA 2018 higher tier. So this is the last question we're on about methanol being an oxidizing agent. So I'll carry on. So part 3, different question. This question is about gases. So not to do with our other question now. Figure 3 shows how nitrogen is used in the Haber process to produce ammonia. We've got figure 3, nitrogen, unknown gas. I think you probably know what it is if you've seen the Haber process. Reactor, condenser, unreacted has to go back, and we get ammonia out. Okay, so remember ammonia is important to make fertilizers. That's what we're generally making here. Okay, so we're actually using it for a purpose. So name gas X. So you probably all straight away write down hydrogen. It's the same answer. Hydrogen has been a bit of a star so far in this paper. It's come a few times already, hydrogen. Okay. So give the approximate temperature and pressure used in the reactor. So it's just learning this, okay, is the temperature is about 450 degrees. This is a thing to remember. And 200 atmospheres. So 200, as long as we're in ATM. That stands for atmospheres. Often you'll see it in ATM, atmospheres. Okay. The mixture of gases from the reactor cools in the condenser. Suggest why ammonia condenses, but the other gases do not. Because ammonia has a higher boiling point. It's a bit like the fractionation column, really, for oil. So of the fractions of gases for oil. So it has a higher boiling point. Okay. So let's go to the next one. The Earth's early atmosphere was different to Earth's atmosphere today. Scientists think that the Earth's early atmosphere was like the atmosphere found on Venus today. Okay, so Venus is actually our closest planet to us. Table 2 shows the amount of carbon dioxide and oxygen in the atmospheres of Venus and Earth today. Okay, carbon dioxide in Venus's atmosphere, 96.5. Okay, 0 oxygen, this is Venus's atmosphere. In Earth's atmosphere, carbon dioxide 0.04, oxygen 20.95, often around at 21, and you'll see that. The percentages of carbon dioxide and oxygen have changed from Earth's early atmosphere to Earth's atmosphere today. Explain the processes, so more than one, that led to these changes. So I've given us a bit of writing underneath. I give you quite a lot of room in the actual paper too. I haven't covered all the lines, just to sort of make my writing a bit clearer. Okay, so explain the processes leading to these changes. So actually, this is quite a nice thing because it's a little bit of a story, isn't it? So in Earth, so carbon dioxide. Okay. So it's just the Earth, so don't worry about Venus, we just have to know about Earth. So carbon dioxide has decreased, okay, on Earth. Because I'm going to write a CO2 from now on, carbon dioxide. CO2 dissolved in the oceans. When you have a fizzy drink, it's because you've got carbon dioxide dissolved in it, because carbon dioxide dissolved in water. It's a really important thing to know. There's another paper that asks about that, carbon dioxide dissolving in water. It dissolves quite easily in water. Okay, dissolved in the oceans. So the water vapor that made the oceans came from volcanoes. So that's a little bonus bit here. So water vapor came from volcanoes and some comets as well. They brought some water to Earth. So you asked about where the water comes from. Okay. So what happened next? So also carbon dioxide. Okay. Produces sediments like chalk like calcium carbonate, it produces sediments. Okay. And rocks. They get squashed down, they actually form rocks. Okay, so it's locked up. So often you hear it as a carbon store. Then the oxygen. So oxygen gave us a bit more room. We can just do this on the computer. They give you quite a lot of room in the paper, so don't worry about ever writing too big. They do give a lot of room. So oxygen increased. Due to all of this one, photosynthesis. So it's actually living creatures change the atmosphere. Increased due to photosynthesis. Algae were the first plants to do this. It's like you find a fish tank or a pond, the same type. Algae took in CO2 and released oxygen, O2. Okay, oxygen. So that was the story. That's actually quite a nice story, 6 mark, and the easiest 6 mark question you've ever seen. Okay, that's a nice one if you get that. You probably get something to do with the Earth's atmosphere at some point, so that's nice and easy. 3.5. Why are scientists not certain about the percentage of each gas in the Earth's early atmosphere? Okay, so not 100% certain, so there's limited evidence. We're going by fossil records here. Limited evidence, okay, as it was 4.6 billion years ago. So it might not be 100% accurate. Okay, now go on to question 4. It's a different question entirely, not about the Earth's atmosphere. A student investigated the colours in 3 different flowers, A, B, and C. The colours are soluble in ethanol, but are insoluble in water. This is the method used. Crush flower A, add ethanol to flower A, filter the mixture. Put spots of the coloured filtrate onto the chromatography paper. Repeat steps 1 to 4 with flowers B and C. Figure 4 shows the apparatus used. The student made 2 mistakes in setting up the apparatus. Give 1 problem caused by each mistake. Oh, okay. Let's have a look. We've got lid. We've got beaker. That's okay at the moment. Chromatography paper seems fine. Start line in ink. Okay, so that was the problem. Is the start line should be drawn in pencil. If it was drawn in ink, the ink could also have pigments in it that run up. Because sometimes you're actually testing pens, aren't you? Okay, so it shouldn't be drawn in ink. It should be drawn in pencil. Okay, and also water is shown as a solvent, but it says they're insoluble in water, so that they won't do anything. So yeah, that should have been ethanol. So let's write that out. So mistake 1. So the start line is drawn in ink. Problem caused. So the ink would run. Okay. Would run in solvent. Okay, and also water used as a solvent. Water used as solvent. So problem caused is that the colours will not dissolve. So from the flower. Okay. Another student set up the apparatus correctly. Figure 5 represents the student's results. Give 2 conclusions you can make about figure 5. Okay, so 2 conclusions. So A's only got 1 pigment in it. So, and B. So A and B only contain 1 colour or pigment. And 2, we'll see contains 2. Okay, we said a mix of colours or 2 colours. Colour A has an RF value of 0.65. Colour A moves 3.2 centimetres. Calculate the distance moved by the solvent. Okay, so it's 3, so distance moved. There's a little bit of remembering this one. 3.2 over 0.65. We're going to get 4.9 centimetres. 1.9. They're giving us centimetres. Okay. Oh, question 5. Sodium thiosulfate reacts with dilute hydrochloric acid. The solution becomes cloudy as the reaction takes place. You may have seen this before in class. The equation for the reaction, sodium thiosulfate plus 2 HCl, 2 hydrochloric acid, goes to sodium chloride plus sulfur dioxide plus sulfur. Explain why the solution becomes cloudy. It's because this sulfur, I was actually about to say that before the question is sulfur. So sulfur is formed. Is formed as a precipitate. Also, you can smell the sulfur. Okay, very distinctive smell of sulfur. It's sort of we've been near a volcano, you know, the smell of it. Formed as a precipitate, so it's insoluble. Okay. 5.2. Plan an investigation to show how the concentration, let's just highlight that, of sodium thiosulfate solution affects the rate of reaction with dilute hydrochloric acid. So we're changing the concentration there. Okay, so we've got a method. So measure we'll say 250 centimeters cubed. That's generally what I used to use. Measure 250 centimeters cubed of sodium thiosulfate. Okay, then place sodium thiosulfate in a conical flask. Yeah, that's important, a conical flask I would use. So add say 100, you just have to give indication, the sensible indication of hydrochloric acid. Remember the formula above gave us a clue if you've forgotten what we needed to do. Okay, so place on white tile with cross. You have something more fancy like a light meter, but I used to use this. Actually, hang on, don't put that. Sorry, it's if you make a mistake like me, I'm not going to add it yet. I should have put measure. So if you make a mistake, just do what I did. Just cross like that. Okay, it's good practice to show measure. So we haven't added. We should have measured it before we added it. I meant to say measure. So and then you add. So add the acid to the sodium thiosulfate. You swirl it. Let's get a little bit of a start up. So swirl and start stop clock. Okay, measure. This is what I did in class. So I was teaching class. Measure the time taken for cross to disappear. So you look down. Okay, so if you find it difficult to describe what you're doing, you can always draw. Okay, so you have a tile. I'm going to draw it sort of half 3D. Yeah, that would, you have a cross. You put the beaker, sorry, the conical flask on it. Okay, and over time this starts to precipitate. Okay, the thiosulfate on its own is colourless, so you can see through it. But when the sulfur starts to precipitate, then you won't be able to see that cross anymore. You'll be looking down. So the eye looking down. Okay, so you won't be able to see that cross anymore. So you can always draw a diagram. That's what I've just done to help you. Okay, because if you sort of think you remember it, you see in your head what you did. Okay, so then you repeat. Okay, with varying concentrations. So that's what we're changing. That's the independent variable. Okay, so control variables. You need to keep the concentration of hydrochloric, varying concentrations of sodium thiosulfate. Okay, I'm going to make it a little bit clearer here. Thiosulfate. Okay, so control variables would be concentration of the acid. So you need to use the same volumes each time. So volume of sodium thiosulfate plus HCl. So total volume for them. Okay, so well done for listening to that. Okay, thank you. Yeah, it takes a while. It's actually not too bad. If you've done this before, you would remember how to do it. Okay, so I'm going to stop this video here. Thank you for listening, and I'll see you in the next part. Thank you. Goodbye.